All right, folks, we are starting a new section of this unit. This one is on gravity, and then the next one is on the normal force. So let's begin. We're going to start with Earth's gravity, and because that's what we know. So on Earth, our gravity that we experience comes almost entirely from Earth. And we'll explain why that is later. But on Earth, we experience a constant force of gravity on ourselves that is based on our mass. So the force of gravity on us, or our weight, is equal to mass times little g, where little g is 9.8 newtons per kilogram. That's not the same units you've seen for 9.8, and so I'll also explain that. The letter little g, or the variable little g, it does mean acceleration, but I want to talk about it in terms of gravity. It also means gravitational field strength. And so it represents how strong gravity is in a particular location. And that location can actually be anywhere in the universe, but little g is typically used to represent the gravitational strength near a planet's surface or on a planet's surface. And we'll talk really a little bit in class maybe about what a field is, but gravity is a force that can operate at a distance. And so objects don't need to be touching in order for there to be gravity. So what does this mean for us? Little g for us on Earth is 9.8. Now, what we experience is a nearly constant gravitational field near Earth's surface. It's not actually constant. And so that's another thing we'll address later in the video, is like, how does the strength of gravity change as you move to higher elevations and as you move away from Earth's surface? And that's it. So that's why we've been using 9.8 for everything, that there's a constant amount of gravity near Earth's surface, and so we can always use this number 9.8. Now, to address the other part of that, the units for G are newtons per kilogram. And as you did in your lab last part of the unit, we took the newton and we put in the units that it represents. So the newton is a kilogram meter per second squared. If I divide that by the kilogram part of the unit, that cancels, and I'm left with meters per second squared. So newtons per kilogram and meters per second squared are actually the same unit. So not only is G gravitational field strength, we already knew that G is acceleration due to gravity. Now, G is a positive number. When we apply it to both gravitational field strength and acceleration due to gravity, we usually use it as a negative number because it points down. The gravitational field of Earth points down. That's why gravity is always the downward force for us. And then we accelerate downward when we are in midair. So when we apply little g to acceleration, it becomes negative g, and so negative 9.8 meters per second squared. But it's going to be important later to recognize that g is a positive number in all respects. All right, so then that brings us to expanding the idea of gravity. Gravity is not a constant force everywhere in the universe, and Isaac Newton figured out a law that describes the force of gravity anywhere in the universe due to two objects. So the idea behind this is that every particle, now by particle, I sometimes mean particle, like proton or atom, but usually I mean object. And we treat objects as if they are particles, and we use the concept of center of mass to do that. So more on that in a minute. Every particle feels a gravitational attraction to all other particles. So anyway, particles mean objects of any size. Gravity is an attractive force, and every particle is attracted to every other particle in the universe due to the force of gravity. And as you'll see in a second, it's due to the fact that every particle has mass. So we'll jump to the equation. Fg is still the variable for gravity, but this equation throws absolute value symbols around Fg. And I will explain that. But here's the whole equation. When you see absolute value signs around a vector, it means that the equation you're using is not capable of determining the direction of the gravitational force. It is only capable of showing you the magnitude. So absolute value signs mean that the equation is for the magnitude of the force, not the direction. The variables in this equation, m1 and m2, are the masses of the two objects. The variable r is the distance between the centers of mass. And so the object that can be any size, but we're going to treat every object as like a uniform object, and so the center of it is going to be how we position the object. That's going to be where the object is. The last variable is capital G. That is the gravitational constant. Gravitational constant is different from little g. It is a number that represents not how strong gravity is in a particular spot, but rather how strong gravity is as a force. This number is 6.67 times 10 to the negative 11th. And so the size of that number tells you that gravity is a weak force. The units are Newton meters squared per kilogram squared. And so that's just a constant you'll put in this equation if you need to calculate something exactly. Otherwise, the communication there is that that number is small, therefore the force of gravity is very weak. We only experience a strong force of gravity because the objects in our solar system and our universe have a ton of mass, and so they create a lot of gravity. All right, so this equation says like the more mass an object has, the more gravity it creates. However, the further away objects are from one another, the weaker the pull of gravity. So we'll more on that in just a moment. Let's like visualize what's happening here. So we're going to have an object that we're going to call M1, and then we'll have another object here that's going to be M2. Now, again, these objects take up a lot of space, so we make the assumption that all of their mass is focused at their center of mass. So these objects are no longer large, they're just single points in space, and then there is some distance between them. And so notice that when I draw that line represents the variable r, represents the distance between the centers of mass. It includes all of the space between the objects plus the radius of these objects. Pretty much every object we're going to use for gravity, we're going to model it as a circle or a sphere. And so part of the distance between the center of mass of the two objects is the radius of the object itself. And so what ends up happening is you get two forces of gravity. So it takes two masses to have a force of gravity. There is a force of gravity acting on M1 that pulls it toward M2. And there is also a force of gravity on M2 that pulls it toward M1. So there are a couple of things about those. Notice that they are opposite direction. That's actually why there's the absolute value sign here. These two forces are in two different directions, and so there's no way that this one equation can tell you the direction of both of those vectors. The other thing is these two objects are experiencing an interaction. So Newton's third law says those two forces have to be the same magnitude. And so that's why they're both in that equation. Those forces have the same magnitude because they are part of an interaction between those two objects. All right, two more things for this little lesson here. The next one is just this general equation here. So this equation has this inverse relationship between the force of gravity and distance. I think my camera froze, so give me a second. There we go. So in that equation, the force of gravity is proportional to 1 over r squared. So we talked a little bit about proportionalities in the lab. We can take an equation and extract the proportionalities. So Fg and r are two variables, and so they have an inverse square relationship. If I were to draw that on a graph, the relationship between the force of gravity and distance between centers of mass would look like this. It drops off very quickly at first, and then it kind of starts to look like it levels off, but it just keeps getting smaller. And what this means is, like, if you put two objects very close to one another, they would have a pretty high force of gravity attraction between them. But very quickly, as you start to move away, that force of gravity diminishes to a very small value. So we imagine that here we are on Earth. This drawing is obviously not to scale, and we are just standing on Earth's surface. We are a relatively short distance away from the center of the Earth, and so we feel a certain force of gravity between us and the Earth. Then we go out into space. If we manage to float away from Earth, maybe we're out in a space station and we're zipping around Earth in orbit. We are now further away, and there is a significantly smaller force of gravity on us the further we get away. So these are the two values of r for this person standing on Earth and this person floating above Earth's atmosphere. The further away you get, the smaller gravity is. The last part of this lesson is about multiple objects, and so I'll try and be quick here. We can have as many objects as we want in our system, and so I'll just show you 3 objects and their interaction. These 3 objects are organized in kind of a triangular arrangement, and the way that this universal gravitation works is that they all attract one another. So object 1 feels a force of attraction for object 2 and also a force of attraction for object 3. So there's a net force of gravitation on object 1 that is the sum of these 2 vectors. The same thing goes for object 2. It is attracted to both object 1 and object 3. And then same thing for object 3. It's attracted to object 2 and it's attracted to object 1. Now these 2 forces right here are probably not the same magnitude because objects 1 and 2 probably have different masses, and then this distance and this distance are probably different values. So the more objects you add, the more forces of gravity exist. I apologize for the length of this video. The rest of this part of the unit should be relatively short. Thanks.